Welcome to Power System Laboratory. So our today's experiment is determination of reactive power for zero voltage regulation at different load using RLC compensation with tap changing transformer and RLC compensation with auto transformer. So as you can see, we have a transmission line here. We have modeled the transmission line of 400 km and each is divided into each 80 km, and we have to short circuit this to form a 400 km transmission line. So what we will do, that we will send the voltage from the sending end and we will receive the voltage and we will apply the compensation, and that compensation will be applied at different value of load. So like when there will be a no load, that time we have to apply the compensation, and when there will be a some load, then also we have to apply compensation. So why we are applying the compensation? To make the zero voltage regulation. Zero voltage regulation means our sending end voltage and our receiving end voltage will be equal. So whenever we are sending some voltage, then here the receiving end voltage will differ. Why that will differ? Because as we know, in a transmission line they are having a resistance, inductance due to the line conductor, and the capacitance due to the line voltage with respect to the ground. So what happens, due to that capacitance and that ferritic effect, we are observing that the without load we are getting the receiving end voltage is more than the sending end voltage. So what will happen in that case? If our receiving end voltage will be more than the sending end voltage, our load will get disrupted, because of load is already designed for some particular range of voltage. If the voltage will be more than that, then what will happen? That will be a disturbance for the load, and in that way the quality of power will be reduced. So we have to maintain the voltage which is going to the load. So for that we have to apply the compensation. So compensation we have to apply, that depends on whether the voltage is more than the sending end or the voltage is less than the sending end. So keeping in that in mind, what we have to see, that we have to apply some compensation. So like if the voltage at receiving end is more than the sending end, then we have to reduce the voltage. So to reduce the voltage, we have to apply the compensation of R and L, because that is the reactive power we are going to apply. Then when there is a voltage which is less than the receiving end voltage, then what we will have to do, we have to increase the voltage. So in this case we have to apply the capacitor or the capacitive reactive power across the compensating terminal. So in this way we are able to compensate the transmission line, and we can able to make the receiving end voltage and the sending end voltage to be equal. But there is a different method of compensation. If you will see, there is a different method of compensation. So one method which we are following, directly the RLC will be connected across the compensating terminal here, and in the next step what we will do, we will use the same RLC compensation through a tap changing transformer. So then we will see how that compensation will be easy, or whether it will be very difficult to operate the compensation, or how much accurate we are compensating. So depending on that we are following different procedure. So as you can see here, RL is there, it will be connected directly across the compensation, and there is a RLC switches are there. By adjusting these RLC switches, we are adjusting the value of R and L, and that will adjust the how much reactive power it will draw from the line. Similarly, if we will have a RLC compensation with tap changing transformer, so what will happen, we have to connect RLC compensation, then tap changing transformer, then to our compensating terminal. So what will happen, we can adjust the tap changing transformer voltage. So by adjusting the different tap, we can have a different voltage, and significantly we can produce different reactive power we can draw from the compensating terminal. Similarly, another is the tap changing transformer will be replaced to auto transformer. So what will happen, the RLC compensation through a auto transformer. So we will adjust the auto transformer voltage, and smoothly we will adjust the auto transformer voltage, and the reactive power which is required to get zero voltage regulation, that can be achieved easily through the auto transformer method. So that we will see when we will do the experiment. In this experiment we will see that which method will give us accurate zero voltage regulation and faster zero voltage regulation, that we will come to conclude after completing this experiment. But before that, let's see details about the panel or the details about this equipment which you are going to use in this experiment. So here, as you can see, this is the input sending end side. So in the sending end side, there is a variac is connected, and at the output there is a circuit breaker, and that circuit breaker switch can be adjusted through this switch. If we will turn on this switch, then the circuit breaker will connect the variac from this end to the sending end of the transmission line. So this is a single phase transmission line. This is a duplicate of single phase transmission line. That's why only phase and neutral are present. Then after this circuit breaker, we will see that there is a power analyzer that is connected internally, and this is the power analyzer which is connected at the sending end. So this power analyzer will show the voltage and the current, the power factor, reactive power, then real power, then apparent power, all different things we can see through this power analyzer. So that is connected internally at the sending end. Then you can see this is a pi section of the first 80 km transmission line. So here this C was the one side of the pi, this C is another side of the pi, C1, C2, and the middle one is R1 and L1. So similarly, we are having 5 pi section. So if we will combine all 5, then we will have a transmission line of length 400 km 220 kilovolt transmission line. Then at the output, here this is the compensating terminal. So from here we will connect the compensation, and from after that there is a circuit breaker CB2. So as you can see, there is a circuit breaker switch CB2. If CB1 will be pushed, then the circuit will be connected from the source and sending end will be connected to the source, and if CB2 will be connected, then the receiving end of the circuit or of the transmission line will be connected to the load. So we will connect the load across these two terminals, and we will connect the compensator across these two terminals. And here there is no power analyzer is connected, so we have to connect externally this power analyzer. So we need a power analyzer in the load. So the circuit is going to the load, so in between you have to connect a power analyzer. We can select this one let, and another power analyzer which will be connected to the compensator. So we will use this power analyzer for compensator power. So we can measure QC and PC through this, and we can measure the real power or the load power through this, and we can measure the sending end parameters through this power analyzer. So these 3 power analyzers we are going to use, and this is the transmission line we are going to use, and this is the RLC unit 1. This is the RLC unit 1. This will be used for the compensating power, and this RLC unit 2 will use only RL and to make the to supply the load. So as you can see, this RLC unit 2 having different switches and RLC unit 1 having different switches. So these switches will be used to adjust the load requirement, and these switches will be used to adjust the compensating requirement. Here these are there. If we will make this switch to off position, then all are off. So accordingly, as per our requirement, we will turn on the load, we will turn on the R, we will turn on the L, we will turn on the C to apply the desired amount of reactive power. Then there is we will use the R and L. This is the L, this is the C. We will not going to use C, only you will use the R and L, and according to our power requirement or load requirement, as per our procedure, we can turn on the 100 watt switch, we can turn on the 200 watt switch, we can turn on the 400, and as per our requirement we can able to turn on the switch. So in this way we are going to apply the load, and using these switches we are going to apply the compensation. And then as we know, here there is this is the terminals of the tap changing transformer. So as you can see, this is the input C and 220 110, and there is an output at different position. So if we will give from the compensating terminal, if we will give to this input and the output of the tap changing transformer, we will connect to RLC unit 2 or RLC unit 1, that is the compensator terminals. So in that way the power will be compensating power will be flown from this transmission line through the tap changing transformer and to the compensator, and we can adjust the compensating switch terminals or the compensating position or the tap changing position through this switch. This is the transformer tap selector. So as you can see, by selecting different position 1, 2, 3, 4, we can have different position corresponds to different voltage. So 1 corresponds to 100, 2 corresponds to 130. Similarly, at position 8, we can have 240. So in this way, in the step format, we can adjust the output voltage of the tap changing transformer, and depending on the output voltage of the tap changing transformer, the power will be flown from the compensating unit, from the transmission line to the compensating unit. And there another is the Reactive, so that is the auto transformer 2. When we use the third procedure, there we have to connect the compensator through the auto transformer. So here, instead of having tap changing or the step change of the compensating power, we can have the variable change. So here uniformly we can adjust the position of the variac and position of the auto transformer, and we can adjust uniformly the requirement of compensating power to compensate the receiving end voltage to make equal to sending end voltage. So these things we are going to use, like RLC unit 1, RLC unit 2, and this auto transformer, and this tap changing transformer, and the transmission line, and there is a CB1, CB2 and CB3 also will be used when we will use the tap changing transformer. As you can see, there is a CB is connected, so if you use tap changing transformer, there you have to use the CB3. If you use the variac or the auto transformer, there no circuit breaker is available. So before starting the experiment, we have to do some connections according to our circuit diagram. So let's see how we are doing the connection. So as you can see here, this is the source. So here using variac 1, we can adjust the voltage at here. We can adjust to 20 volt to 30 volt depending on the position of the variac, and that voltage will come to this transformer, isolating transformer, and at the output there is a circuit breaker. So if you turn on, then that voltage will come here. So right now we'll start the connection from here. So here already this wire is connected, so this is connected, and this is connected. So what we have to do, we have to connect this with this, because this capacitor have to connect with this terminal. So we have to use this wire so that this capacitor is connected. Similarly, here also we have to do like this capacitor we have to connect, and also this capacitor also we have to connect, and at the same time we have to connect the two transmission line from here to here. So if you see the circuit diagram, you can easily understand what we are doing here. So similarly here these two will be connected, and these two will be connected, and this and this. Next here is like same, these two, these two, then this and this. Similarly this, and this. Basically we are connecting all the pi, and we are making the 80 to 400 kilometer transmission line. And here in the bottom side, as you can see, we have to connect these two. Similarly these two, similarly these two, and this is already connected. Only you have to connect this to here. we will connect the compensator at these two terminal and we will connect the load at these two terminal. So the compensation here RLC unit 1, we will use the R1, L1, C1 and here also unit 2, L2 and C2. These all will be used for the RLC compensation and only this R2 will be used for the load. So now we will connect the compensation. How we will connect? So here this RL we have to do in series. So this RL and this L1 and L2 will connect into parallel, because if L1 and L2 will be connected in parallel, so it will draw more reactive current when both will be connected. So this L1, so this will come here and here. So this L1 and this L2 are parallel and it's connected with R. Next, this RL will be connected in parallel with a C, that is C1, and also same time to increase the capacitive reactive power we have to use the C2, and that C2 also will be connected in parallel with the C1. I will show this connection in the video how we are doing the diagram of the connection. So this C2 is connected parallel with C1. So how the circuit is? The R1 is in series with L1 and L2 parallel, and both RL is connected in parallel with C1 and C2, and these two terminal will be used, or these two terminal will be used for the compensation. So we will use another two wire. So this red, this black will connect to here. So in this way our compensator is connected. So this R1 is connected in series with L1 and L2 parallel, and this RL parallel is connected with C1 and C2 parallel. So you will see the diagram, then you will come to understand. Then we have to connect this load. So we will connect the R2 of the RLC unit 2 for loading. So this plus, this minus, or this phase and neutral will be connected to this R2. So now the load also connected. So as you can see, but also we can see that we are connected directly without any power analyzer. Now we will connect the power analyzer. So as you can see that this is the V1 and V2, and this one I told you we will use for the compensation, and this one will be used for the load power measurement. So this V1 and this V2 and this S1 and S2 is the current terminal. So what will happen? So the current which is flowing to the compensator will be flown through this power analyzer. Then the input of the power analyzer will be connected to output of the compensating terminal. So how power is flowing? So from the transmission line it is going to this meter, and then the output S2 is connected to here, and the neutral is directly connected to here, and this voltage we have to connect these two terminal voltage across the compensating power. So one neutral, this is the V2 is the neutral, so we'll connect here, so both are same, so neutral, and the phase which is going to the compensator, that we will use. So we can use a small wire instead, like this and like this. So as you can see, this power is flowing from the transmission line through the meter, and it is coming to the compensator, LC compensator, and this voltage we are measuring across the output or the input of the compensator. This is the P or the phase, and this is the neutral. This connection is for the compensator. Now we will do the connection for the load. So similarly, this positive will go from this S2, and this phase will go to S1. So phase is going to S1 and S2 is going to the load, and this phase voltage will be connected at the output of the power analyzer. Then this one, which is the neutral, will be connected to here. As you can see, this is the neutral of the load. This is the phase and this is the neutral. So this phase is coming to this power analyzer, then output of the power analyzer is going to the R, then the neutral is coming to the here, and at the same neutral is coming to here, and the voltage V1 is connected to here. So in this way, this meter will tell us the power of the load, this meter will tell us the power of the compensator, that means QC and PC. As you have noticed that we are telling that the compensator must be inductive or reactive, because if it is inductive it will draw the reactive power, if it is capacitive it will feed the reactive power. And what will happen at last? If the compensator will feed the reactive power, it will increase the voltage, and if it will draw the reactive power, it will decrease the voltage. So, but here the L, that is the inductive reactive power, we cannot connect directly across this terminal. So, we have to use the R in series with L. So if R will be connected in series with L, then what will happen? There will be some power loss in the R. So that we have to use, that how much compensation we are applying and how much power is utilized to get the compensation. If there is a C compensation, means there is a capacitive power compensation, there will be no power drop in the resistor. But if there will be inductive compensation, then there will be a power drop at the R. And you will see, by increasing the load from different 0, no load to 100, 200 or from 300 watt, we will see the requirement of L reactive power or the inductive reactive power will be reduced, and the requirement of capacitive reactive power will be increased. So what will happen? At particular value of compensator, we will see that our sending end will be equal to the receiving end. And one thing also you will notice that every transmission line has a SIL, that is the surge impedance loading. So that at the another experiment where we will find what is the surge impedance loading of the transmission line, and by knowing the surge impedance loading we can conclude that if we will apply that much load across the transmission line, what will happen? At that condition there will be no requirement of compensator, but we will get zero voltage regulation. So that is the SIL. So what will happen? If we will increase the load from 0, it will increase and it will reach the SIL, and if the load requirement is more than SIL, then we need the reactive power compensation, that is the capacitive reactive power compensation. And if the load is less than SIL, we will observe that we need inductive reactive power compensation. So now we will perform the experiment. So as I have told you that this power analyzer will be used to measure the compensating power, that is QC and PC, and this power analyzer will be used to measure the power going to the load, that is the resistive power, that will be shown in watt. Then to make sending end voltage equal with the receiving end voltage, we also have to observe the receiving end voltage. Here also we can observe the receiving end voltage, because this is the power analyzer. This can measure voltage, current, power, all these things. But here right now it is showing voltage. Now to see the power, we have to again press another this button, this button, this button. Then this screen will show us the this real power, and this will show us the inductive reactive power, and this one will show us the capacitive reactive power. So this screen will tell you that. Similarly, this screen will tell you the power flowing to the load. But to know the voltage, again you have to press. So already we have another power analyzer which is blank. So we can use that to note down the receiving end voltage. So as you can see, I have connected this only V1 and V2 terminal to measure the voltage only. So this will tell my sending end voltage, this will tell the receiving end voltage, this will tell my QCPC, and this will tell my load power. So I will connect this across the here. So I have connected. So this will measure my receiving end voltage, sending end voltage, QC, PC, and this real power flowing to the load. So now in the procedure, we have to apply 220 volt at the transmission line. So as you can see, there is a circuit breaker. We have to turn on the circuit breaker first. So after turning on the circuit breaker, we can adjust the variac, and the voltage will come to here, and this will come to the meter as well, and this meter will tell the voltage. So I will increase here, and there you will see the voltage will increase, and we will keep the voltage to 220. So right now it is 39, 41, 59, 68, 70, 120, 145. Will maintain the voltage to 220, because this transmission line is designed for 220 kV transmission. So we are simulating all those things in voltage. So we are applying the 220 volt. So this is to 10 to 15 to 20, little less. So 220. So 220. So as you can see, our sending end voltage is 220, and we have not connected any load because the circuit breaker CB2 is turned off. So this is the no load condition, and the compensating power voltage or the receiving end voltage is 243, which is more than the sending end voltage. Now as I have told you that to compensate or to make zero voltage regulation, we have to make this 220 and this also 220. This is already 220, so we have to make this 220. So what we have to do, we have to apply the RL compensation to reduce the voltage to 220. So now these are the switches of R and these are the L. So we will turn on this R, all R switches, and we will increase the L. So one L voltage reduced to 240, another switch it is reduced to 238. Similarly, we will try to turn on the switches of L. As you can see here, I have used all the switches available for L1, but also I have connected L2. So again, I can turn on the L2 switches so that it will draw more reactive power. So right now I have turned on these 7 switches, and it is drawing reactive power, and it is showing that 227. So then we have to turn on this once again, 224, again turn on once again. As you can see, voltage equal. So right now our sending end voltage is equal to the receiving end voltage, but the sending end is reduced to 219. So by adjusting variac 1, so we will again little bit we can increase to 220. Okay. So this is 220, this is 220. And right now here you can see that this is the real power and this is the reactive power taken by the compensator. This is the PC and this is the QC, and this is minus, it is showing means the connection is reversed. That's why the P is minus and the Q is also minus. This Q, if we will reverse the connection, this P will be plus, this Q will be plus, but this C, that is the QC of capacitor reactive power, will be minus. So we can note down in plus, so that this is 60, our PC is 60, and our QL or reactive power QC, compensating power QC is 59 plus 59. And as you can see here, the no load is not connected, so this is showing 0. So now we will connect the load. So before turning on the load, we have to turn on the circuit breaker 2, and after turning circuit breaker 2 also it is showing 0, that means load switch is not connected. So now we will connect the 100 watt load. So I have connected the 100 watt load. As you can see, it is showing near around 100, and the voltage is reduced to 209. So again we have to reduce the L compensation. So we have to reduce the L compensation. Our voltage increased to 212. Again this, that is 212. Again this 214. Okay. 217. Okay, now it is equal. So if you will see, we are applying 24 watt of real power, that is PC, and QC is 31, and at that condition and at 100 watt of load we are getting this 0 voltage regulation, that means 220, and this is 220. So we have applied some value of compensation here, and we are getting 0 voltage regulation. Now we will increase the load to 200. So I will turn off this 100 switch, turn on this 200 switch. So as you can see, I have applied 200 watt, but still you see our voltage is reduced. So what we have to do? We have to reduce the compensation. So I will turn off L, and as you can see here, I have told you that I have turned off all the compensator. This R is off, L is off, C off, all those, only load switch is connected, and that is near around 200 watt. And you will see this sending end voltage is equal to the receiving end voltage, and there is no compensation is applied. That's why these two are 0. But we are getting 0 voltage regulation. So this is the condition of SIL. If we measure the transmission line in a different method, ABCD parameter method, the SIL, there we will find that 200 watt is the SIL. And right now we are applying 200 watt of power, and the sending end and receiving end becoming equal. Now we will increase the load, and as I have told you that if we increase the load above SIL, we need the capacitive reactive power to make 0 voltage regulation. So now I will turn on the 100 watt switch. So now power becoming 200 and 300 watt, and as you can see here, our voltage is again reduced to 203, and we need the capacitive reactive power to increase the voltage. So I will turn on the, this is the capacitor. So voltage is increased to 206. Once again voltage is increased to 209, and voltage is increased to 219. So I will reduce this. So 217. So right now our sending end is equal to receiving end. We can increase the sending end to make 220. So that I will do. I will increase this 220. Our sending end 220, our receiving end 220, and we are applying 300 watt of power. And here you can see the real power is almost 0, and the reactive power that becoming 75. This is the plus. This is showing plus. So that means this is the capacitive reactive power. Earlier it was showing minus. So that is the inductive reactive power. We can write this as minus because this is the QC of capacitive reactive power. Earlier that is Q for the inductive reactive power. So this is the first method for the compensation without any tap changing transformer or auto transformer. Now we will change the compensator, and we will connect the compensator through the tap changing transformer, and we will try to compensate with this 3 load, and we will see how the compensation is applied. So we will turn off all those things, and again we will start from the beginning. So now we will do the next procedure. So that we have to connect the compensation through the tap changing transformer. So as you can see, our circuit breaker, these two are off, so no power supply is coming to here. So we have to give the output of the tap changing transformer to the input of the compensation. So as you can see, I am giving this output, and the input which is coming from the power analyzer. This is the input of the power analyzer, input of the compensation. So these two are the input of the compensation. So these two I am giving to the output of the tap changing transformer. Next, the output of the power analyzer will be connected to input of the tap changing transformer. And input of the power analyzer is already connected. This tap changing transformer is already connected in series with the compensation. So what will happen here? So this will be connected to the output of the power analyzer plus, and the negative is common. So negative we can connect that here. Neutral we can connect that here. So as you can see, this blue wire and this yellow wire, these two are the input, and the output of power analyzer is the red wire, and this black one which is already connected to the neutral. Next, the output of the tap changing transformer is from this red and black is going to the here, this red and black, that is the input of the compensator. So right now the RLC unit is connected through the tap changing transformer. Now we will apply the supply, we will turn on the circuit breaker 1, 2, and we will adjust the voltage, and we will see how we are going to compensate. Right now if you will see, our tap changing position is set to position 1. So that is the 110 volt. So if we will increase the tap changing position from position 1 to position 8, it gradually increases the voltage, that is 110 to 130, 180, like that it increases the voltage. And as you know, if the voltage will increase, then the current will also increase and the power will increase. If the output of the tap changing transformer will be having only RL, then by increasing the tap changing or the tap changing position, we will have the more value of reactive power, so that the voltage will go down if the secondary of the tap changing transformer will be RL. If the secondary of the tap changing transformer will be capacitive, so what will happen? If we will increase the tap, then the reactive power, capacity reactive power will increase, and this will increase the voltage at the receiving end. So that means this tap changing position, what it will do, it will help to increase the power which is the compensator or the RLC unit is taking. So let RLC unit is taking the power of let 100 var. So now to increase the power from 100 var to more, we have to increase the tap changing. So we are increasing the voltage across the compensator, and that significantly or indirectly it increases the power which will be taken from the transmission line, that is the reactive power. Now we will turn on the circuit breaker. So circuit breaker 1 we have to turn on. So after turning on, we have to ensure that at the sending end voltage should be 220. Right now it is 221. So let me increase the voltage or decrease the voltage to 220. So this is the 220. Now if we will see that circuit breaker 2 is off. So if circuit breaker 2 is off means our load is disconnected, and load is disconnected, that means this is a no load, and in this case we are getting 231 for the 231 at the receiving end, and the primary terminal of the tap changing transformer is connected across the compensator unit. So that's why, and the secondary is turned off. As you can see, there is another circuit breaker is present at the secondary side of the tap changing transformer, and which is turned off. So this primary side is only connected, and due to the primary side winding R and L, it is taking 32 watt of real power and 48 watt of reactive power, and due to that power we are getting voltage of 230. So now we have to make zero voltage regulation at the no load. So what we will do, we have to turn on the circuit breaker. We have to turn on the circuit breaker 3. So if you are turning circuit breaker 3 means compensator or RLC unit will be connected across the tap changing transformer, and we can turn on the corresponding, because we have to reduce the voltage, so we have to turn on the inductor. So right now we have, because R is already on, you can see I am doing, I am turning on all the R, only I am adjusting the L and C, because R is connected in series with L. So if L will be available, then R will come into picture, otherwise there will be no effect of R. So right now let me turn on some value of L. So I turned on some value of L, and after turning on, as you can see, our sending end voltage and receiving end voltage becoming equal, and as you can see here, our power, the real power taken from the compensation, that is PC, is 108, and QC, that is the compensating reactive power, that is 41 kilo or 41 var, that is the inductive reactive var. Now you can see here the load is 0, so that means that is the open circuit. So now we will increase the, we will apply some load. So if we will turn on the circuit breaker 2, as you can see, I have turned on the circuit breaker 2, which is showing here, and I have to apply some amount of load. Let me apply the load of 100 watt. So as you can see, I have applied some amount of load of 100 watt, and our sending end voltage is reduced to 217. So let me increase the voltage to 220. Because why I am maintaining the 220? Because the 100 watt will come into picture when the voltage will be at 220. So right now voltage is, you can see 209 at the receiving end. So because voltage at the receiving end is less, that's why power is less. If I increase the voltage to 220, then this will be coming, will become to 100 watt. So now to increase the voltage, earlier we have turned on the inductor. I will turn up the inductor right now. Right now in the RLC part there is no inductor or no capacitor is connected, only the transformer is present. So right now, due to the transformer internal R and L, it is taking 30 watt of real power, 39 of reactive power, and right now our voltage is equal, and at this point we are getting 100 watt of power. So this is the another, like without having RLC, only the tap changing transformer is giving us an extra real power or the extra compensating power for the transmission line. And we can, as you can see right now, as I have told you that in the secondary side of the tap changing transformer we are having RL, but right now there is no RL is there, all are off. So the internal or the primary side winding is taking this much power. If I increase the power to let 200 watt, so as you can see I am increasing the power to 200 watt, so it is near around 200 watt because our voltage is reduced. So we have to increase the voltage. So what we have to do, we have to increase the voltage. So to increase the voltage, I have to turn on the capacitor. So let me turn on some value of capacitor. Still voltage is not that much. So let me turn some other value of capacitor. Let this one. So let this one. Okay. So as you can see, I have turned on some 3 value of capacitor, and I am getting here 220, and because here I am getting 220, that's why here we are getting 200 watt of power, and here this is the 32 watt of real power, and there is a capacity power is the 25 var of capacity power. So this QC we can write, when there is a capacity power we have to write that is a minus value, minus of Q. Earlier which we are seeing here, that is the plus, right now we will see the minus, that is minus 26 var, and here this is plus 32 watt. Similarly, if you see what the tap changing benefits, so like if you see our voltage is already adjusted at 0 voltage regulation 220 right now, and the output or the secondary side of the tap changing transformer is connected to C load. So if I increase the tap changing position from 1 to 8, so what will happen? Our voltage will increase. So you see I am changing the position to 1 to 2, and our voltage is increased to 224. So that means this tap changing transformer will give us extra real power requirement for the transmission line, because it reduces it adjusted the voltage at the secondary side, which is indirectly adjust the real power reactive power requirement or compensating power requirement of the transmission line. That means we can have another step of additional step of variation, so that we can able to compensate any value of our power compensation requirement. So let's see, we will turn on some 400 watt of load. So right now I turned on 400 watt of load, and right now you see our voltage is reduced to 194. Now if I increase the voltage, then what I have to do, I have to turn on some of the capacitor. After turning, it is not becoming 220. So let me turn on all value of capacitor. So as you can see, I have turned all value of capacitor, but still my voltage is not equals to sending end. So what I have to do, I have no option in my hand. So what I have to do, I have to again increase the tap changing position to increase the voltage. So you see, voltage is near around 223. So let me adjust the voltage to 223 and reduce some value of capacitor. So after adjusting some value of tap position and some value of capacitor position, I am able to adjust zero voltage regulation. I am able to maintain zero voltage regulation, and here primary side is 214, so I have to increase to 220. So it is 220. Okay. So right now here you can see there is a load of 400 watt, and the reactive capacitive reactive power requirement is minus 207 watt, and real power is 34, and I am getting the voltage to be equal. This is the experiment or procedure 2, and here we have observed that earlier when you have connected only RLC unit, where RL is connected in series and C connected in parallel, and when you have connected that RLC unit as a compensator, in that case what happened, up to 200 watt we have to adjust R and L. So what happens, we have to adjust R and L, means we have to compensate through R and L. So that's why there will be some power loss in the R. Now with the use of compensator or with the use of this tap changing transformer, as you have observed that at 100 watt of load, after 100 watt of load, we have to turn on the capacitor. As you can see, earlier after 200 watt of load, we have to turn on the capacitor. Right now, after 100 watt of load, we have to turn on the capacitor. So one of the advantage here, that if capacitor will be there as a compensator, then there will be no loss in the resistor. So that means there will be a less power loss. But if RL will be there, that means there will be a power loss on R, which is less if you are using the tap changing transformer. So this is the advantage we got if we are shifting our regular compensator, that RLC, to RLC with tap changing transformer. So now we will proceed for the this compensator with auto transformer. So like that, we have to turn off all the circuit breaker, and here this is the input of the tap changing transformer that will change to the auto transformer input, and output of the tap changing transformer will be connected to output of the auto transformer or variac. So as you can see, instead of this tap changing transformer, we are using the auto transformer, and we have to connect the, or we have already connected the RLC unit at the output of the variac or output of the auto transformer. Now we have completed the tap changing transformer RLC unit with tap changing transformer. Now we have connected the RLC unit through auto transformer, and we have to turn on the circuit breaker 1. So after turning circuit breaker 1, our primary voltage or sending in voltage is 226. Let me reduce to 220. So I reduced the voltage to 220 and my CB is off, CB2 is off. So CB2 is off, that's why the load is not connected, that is open circuit at no load, and we are getting the voltage of 240. So right now we have to decrease the voltage to maintain zero voltage regulation. You can see here RLC unit is there, and let me turn on only one switch of the L. Only one switch of the L I have connected. Now to compensate this voltage, what I have to do, I have to adjust the output or the variac position so that our sending end will equals to receiving end. So you can see when I am increasing the output voltage of the variac, so it is increasing the reactive power, that is inductive reactive power, and it indirectly reduces the receiving end voltage, and at particular position of the or particular output voltage of the auto transformer, you will get the sending end voltage will be equal to receiving end voltage. So as you can see, I am increasing and our sending end is becoming equals to receiving end. Okay. Right now it is equal, and I have to increase this voltage to 220. So 220. So as you can see, our sending end is 220, receiving end is 220, and there is no load, and we are getting the real power of this and the reactive power of this, that is the inductive reactive power. Now we will increase the load. So before increasing, we have to turn on the CB2, and after turning on the load or turning on circuit breaker 2, I have to turn on some 100 watt load. So I have turned on 100 watt load, and here it is showing near to 90. Now you can see that this 219 and this voltage is reduced. So I have to increase the voltage. So I have to increase the voltage means, you can see I have to turn up the inductor, and I have to reduce the voltage, or I have to yes, I have to reduce the voltage. Okay. So as you can see, here once again I turned on the inductor. As you can see, I only adjusted the output voltage of the auto transformer. By adjusting the output voltage of the auto transformer, here I am getting that this sending end is equal to receiving end. And you can see here our 100 watt is the power of the load, and our QC is 10 and PC is 73, and QC is still reactive power, that is the inductive reactive power. Now again, if I will turn on some more load, let 200 load, so our load is near around 200, and my voltage is again reduced. So I have to increase the voltage. So what I have to do? First I have to try to reduce the voltage, output voltage of the auto transformer, and I will try to make the sending end to be equal to receiving end. So as you can see, I have turned off or I made the output voltage of the auto transformer to be 0, and still our voltage is not increasing. So I have to apply some value of capacitor, and I have to increase the output voltage of the auto transformer. So as you can see, I have applied 200 watt of load, and I have applied only 11 var of capacitive reactive power, and I made equal sending end to be equal to receiving end. And here as you can see, I have to adjust only the variac position or output voltage of the variac, so that I can adjust the smoothly, I can adjust the ascending end to be equal to receiving end. So now if I increase the load once more, let above 200, let I have to turn on 300. So you can see I have turned on 300 and here voltage is 206. So I have to increase. So what I have to do? I no need to turn on capacitor once again. Only I have to adjust the output voltage of the auto transformer. So by adjusting the output voltage of auto transformer, I am getting there is 0 voltage regulation. So that is 220. So it is near around 220. So I am applying 300 watt of load and I increase the capacitive reactive power, that is 90 bar, and I made equal this sending end to receiving end. And only I am adjusting the output voltage of the auto transformer. Similarly, if I will increase the power 300 to 400 watt, so as you can see, again we have to increase the voltage. So I have to increase this output voltage of the auto transformer. So I have adjusted the output voltage of the auto transformer and I am applying 400 watt of load, but I am getting 0 voltage regulation and this taking 197 of reactive power. And this is our last procedure which we have observed through auto transformer. And we have observed that only by changing a fixed position of the capacitor or the reactor, we are able to adjust 0 voltage regulation. So we have completed all 3 procedures and we can conclude that the procedure of auto transformer compensation is better than the procedure of tap changing transformer or directly RLC. How it is better? Like if we use the RLC, we have to turn on or turn off a different position of the RLC, so that we need more number of RL or C. But in case of auto transformer, only a fixed value of LC or fixed value of inductor and capacitor, and by adjusting the output voltage of the auto transformer, we can easily make 0 voltage regulation. So from this we have concluded that this adjustment of compensator through auto transformer is better than these all 2 compensating methods. So this is about this experiment. We will see in the next experiment.